I'm Adrian. So today I'm going to talk about how I implement Rubik's Cube formula in PyCuber. So if you're interested in my slides, you can I provided a bit.ly short link if you want to. Okay, so a quick introduction to myself. I'm currently a junior high school student, and I have only 1 week to say I'm a junior high school student. So, and I'm currently 9th grader. So, yeah, next week I'll be graduate. And I'm currently a homeschooling student, so I don't go to school every day because I wanna write Python. And so I'm a learning reinforcer at Agile Learning. So most of you don't know what learning reinforcer is, because everyone in Agile Learning has a weird job title, like something like learning supervisor, nearest neighbor, or so I'm just a core developer of Agile Learning. And my other interests besides coding, I really like classical piano and especially Mozart. Okay, so here's today's agenda. So first I'm going to talk about why and what's PyCuber, and then I'm going to talk about several parts in PyCuber. So which part I implemented. And next I'm going to talk about Rubik's Cube, the Rubik's Cube, introduction to Rubik's Cube, and also the Rubik's Cube notations, and then how I implement it in Python. And if I have some extra time, I'll talk about some things about Rubik's Cube, some interesting facts. Okay, so to be honest, this project is actually just for fun. And because I was a very normal student when I'm writing this project, I go to school every day and I do all the homeworks. So I just use my free time and wrote this project. And so back to the topic, what's PyCuber? So PyCuber is a Rubik's Cube Python package. So actually you can pip install PyCuber. And it provides some useful APIs for like cube and formula we'll talk about today. But this project is just for fun, so I didn't consider the performance as the first place. Okay, so here's some parts in PyCuber. So mainly it has 3 parts. So the first one is cube.py, which is implementing the Rubik's Cube itself and how it's positioned. Like a Rubik's Cube has 26 different, well, we call it cubies, which is a small cubes, and how it is turned, how it is twisted, and so on. And the second one is formula, which is we'll talk about today. And the third one is solver, because PyCuber has a built-in solver, which is using a solving Rubik's Cube, a method for solving Rubik's Cube called CFOP. And we're not going to talk about this today. Okay, so I think most of you already played a Rubik's Cube before, but unfortunately I didn't bring a Rubik's Cube today. But I can play a Rubik's Cube from the terminal. Okay, so let's say that's a Rubik's Cube, and you can actually turn it. I'll scale it up like this, and this is not a project I'm writing. It's really interesting. Okay, so a Rubik's Cube is originally invented by Rubik 1974, and he is a professor of the architecture, and he invented this for teaching about some three-dimensional architecture. And so this is what a Rubik's Cube looks like. And it has 3 times 3 times 3 small cubes, and every face has a different color in it. So, a Rubik's Cube has many variations, like Rubik's Revenge, which is a 4 times 4 times 4 Rubik's Cube, and this is Professor's Cube, which is 5, and the biggest one is the over the top cube, which is 17 times 17 times 17, and don't forget the 2 times 2 and 1 by 1. So, okay. So next, I'm going to talk about the notations of Rubik's Cube, because many people they developed their solving methods, and they want to record it and write it into a structure. So most common one is called Singmaster notation, which is developed by David Singmaster, and this is very commonly used in the net. So these are the basics. A step always contains a symbol, a main symbol, which represents the face it was turning. So for instance, R, the R symbol stands by right, and L is left, up is U is up, B is bottom, F is front, B is back. So a R turn, which looks like this, and it always turns clockwise. So you're gonna see the right face, the face on your right hand side, and it is turning clockwise. So it's turning up. Okay, so it's basically a R step. And this is a L. Oh, and there's no animation playing. Okay, yes, here we go. This is a L turn, which is the face on your left hand side, and you're doing clockwise. So it will look like this. And so this one is U turn, which is the up or top layer of your cube, and it is turning clockwise, as you can see. And the D turn, which is the bottom or down, is the bottom layer, and it's turning clockwise. And the F turn is turning the layer on your front. So it will look like this. And the B turn is turning the back of your cube. So in this case, it's turning clockwise. So if the examples here are all turning clockwise, but what if I want to turn it counterclockwise? So a counterclockwise move we will add a prime symbol on it. So like F prime is turning the layer on your front, but instead it is turning counterclockwise. So it's the same as U prime or R prime or L prime. But we also see many about 180 degrees. So to do a 180 degrees, we always use a symbol and following by a 2. So in this example, it is U2, which is turning the top layer and turning 180 degrees. And it was same as F2 or B2 or D2. Okay, so next I'm going to talk about the Y turns. So what is a Y turn? Y turn it just means instead of turning a single layer, I'm turning a double layer. So it will look like this. So the representation of the Y turns, we always write the symbol as it's the same as the single layer turn, but with the lowercase letter. And it will look like this. So a lowercase r turn will doing like this. So your right hand side, and you're turning 2 layers, and it is turning clockwise. And same as L. So in this case, it's lowercase l, and it's lowercase l prime, so it is twisting counterclockwise. And in this case, this is D2, which is turning the bottom layer, but with 2 layers, and it is turning 180 degrees. Okay, so and another part is the whole cube rotations, which is like you're doing a whole cube rotation like this. So what it means, the X means that say there is a X and Y and Z axis. So the X axis is pointing to your right, and Y axis is turning on the top, and the Z axis is pointing toward you. And it will be in this case it is rotating a whole cube and using X axis as the center. So in this case, it's turning clockwise, so it will look like this. And so the same case, I applied it to the Y prime. So it will look like this, because it is turning with Y axis as the center. So it is turning counterclockwise. And this one is Z2. So Z is the axis which points towards you. So it will turning the it will rotate the whole cube and using Z axis as the center. So it will look like this, and we got an extra symbol which is 2, and it will turn 180 degrees. Okay, so is there any questions so far? Okay, so it's time for some Pythonic stuff. Okay, so in my implementation of the Rubik's Cube formula, there are 2 separate classes. The first one is step. The step object represents a single step, which is something like L2 or D2 or X prime. And the second one is formula, which is a sequence of steps. So a step object, it has 2 properties. The first one is called the face, which is the main symbol of your action. So for instance, if you're doing F prime, your face is F. If you're doing lowercase d prime, and your face is lowercase d. And following by an extra symbol, which is like prime or 2, or not adding. Okay, so it will represent it as like clockwise or counterclockwise or 180 degrees. It has 3 types. And in this class, I implemented 3 useful utilities, which is, I think most of you already know what this means in the class when you're defining a class in Python. The underscore add and underscore means the function which it will implement in when you're doing a step object plus another thing. So like 1 plus 1, it will do 1 point, 1 and 1 point underscore underscore add underscore underscore 1. So the double underscore more it is multiply, which is it will call when you're doing a times. And the hash method, it will make the object hashable, which is you can save it in a dictionary as a key. So that's most of this. So when I'm doing add, it will add another step, add a step, and these two steps should be the same phase because I'm going to add these two. So what it's going to adding is like I add a f prime and a f prime. It will return a f2 because if you're doing a counterclockwise and doing another counterclockwise, it will be a 180 degrees. And multiply is just like if I do f times 3, it will become an f prime. Because if you're doing 3 times of clockwise move, it will be same as doing a counterclockwise, about 90 degrees. Okay, so I'm going to talk about the formula, which is the formula class is just a sequence of steps. And so it will look like this because it's obviously it's like a list. And so this is the definition of formula, and I want to initialize a formula with these two methods. Okay, so first one is I'm going to initialize with a list of steps, which is really straightforward. And the second one, which is I pretty want to, it's just initialize with a string and contains every steps as a string. So that would look like this. Well, I'm doing this because I think it is really useful when you're doing a web crawler. If you want to crawl a website which contains the Rubik's Cube formulas. So in my solver, I did wrote this, and I crawl a website. I crawl a tutorial website which contains a lot of formulas, and so I can use it. And so here's several utilities. So first one is multiply, which is it's same as the list multiply, and the EQ means when you're doing comparing, like an object equals to another object, and in this case, I'm going to compare two formulae. I'm going to compare it as their length. I'm using their length because because every step it don't have their own value, because I can say like R prime is bigger than F prime. So I use the length because we always want to find the shortest formula. And the same thing as the less than. So here's some methods which existing in lists, but I'm going to rewrite this in a formula object. So here's append, insert, count, remove, and double underscore contains double underscore. So why I group these together? Because I want to do is if you're doing formula.append, straightforward, and you must add a step object. But I want to add a string like this. So I wanna do f dot append b prime, which the b prime is a string. So in these cases, the inputs are always a step. So the most straightforward method is to write the append method and transfer the input as step object, and then pass it into the super of the formula and call it append. But this is too boring. I want to do something fun, so I wrote a decorator here, and this decorator does is that this decorator is called stepify, which is converts the function's input to a step object. So the implementation is like this. So I get the super function, which is the list method, like append. I got the list.append, and wraps it, which is the function in the functools. And the wrapper function is that it will take as arguments and convert the last argument as a step, so and pass it into the super function. So why I'm doing this? Because I can do it like this. I can do just add stepify and define an append function and just pass it. So it will do the thing I'm expecting. So I can append a string, and it will be it as a step object. So another group is the _add and extend. These two methods, why I'm grouping them together, because they are all adding another sequence. So I want to do it like this instead of adding another formula object. So the thing I'm going to do is f plus r prime u prime, which is the r prime u prime is a string which contains multiple steps, which will doing the same as the when you are initializing a formula. And the same thing happens in extend. So the things I want to do is like this. Okay, so I defined another decorator, which is called formulae. This function will convert the last argument as a formula. So it will look like this. It's just the same as the stepify, but I changed the step to the formula. So I can add another formula to the original formula. So then I can do it like this. Okay, but there is a special case, which is the reverse method in list. I can't just use the list reverse as my formula reverse, because I want to do it like this. Because when you're reversing a formula, you have to do the inverse action. So for example, if you are doing a clockwise move, it will turn it into the counterclockwise move. So that is the reverse, because if I did the L2 prime R on a completed cube, and I reverse it, if I do RU2, it will become a really strange, a really weird state. So I'm going to do is like normal, just reversing it, and then I'm going to inverse every action, so it will do the other direction, like this. So R becomes R prime, and U prime becomes U. And the 180 degrees will not change. Okay, so here are some useful methods which are only in the formula. So the first one is mirroring. The mirroring, it will be very handy because the mirroring is like this. So when you're doing a mirroring, what it's meaning is that if you're doing right-hand side work and you convert it into the left-hand side, it's like mirroring. So this becomes very handy. Okay, and another one is random. The random is just is easy for testing. And another one is optimize. Well, the optimize here is not actually making something like 20 moves and turning it to 3 moves. Instead, I'm just reducing the whole cube rotations and reducing the wide actions and reducing the same step actions. So I got 3 steps. So the first one is no wide actions. The second one is no whole cube rotations, and the third one is no repeated steps. Okay, so here I define 3 different methods, which is I only use it privately. And so it will look like this. This is defined in a class. Okay, so if in a normal Python way, well, we are doing like this. It's just adding an underscore in the front of the method. But that's too normal. I want to do it as fun as I can. So I did a trick like this, which is I add the global variables of a function so that the optimize function, it will have a variable called underscore optimize wide actions. So that's a little magic I'm doing in Python. So a function which has a function has a attribute called double underscore globals double underscore. It is a dictionary, and it stores all the variables in that scope. Okay, so the same thing happens on the other two methods. So I can use these 3 methods inside the optimize functions. Inside the optimize function, but the user can't touch it because I did these 3 functions. Okay, so I'm going to talk about some interesting facts about the Rubik's Cube. So Rubik's Cube is already 41 years old, and the fastest solve is by Colin Burns. It's 5.25 seconds. It's even faster than I'm planning what I'm going to do in the first move. Okay, so this record was break at April this year. Before that, it's 5.35, I think, 5.55. And before the 5.55, it is 5.65. Okay, so the fastest one-handed solve is 6.88 seconds by Felix Zemdex. Can you imagine it? It's one-handed, 6 seconds. And the fastest blindfolded solve is 21 seconds. And the time is including when he is memorizing the cube. So the total time is 21 seconds. It's even faster than I'm solving I use a normal method to solve a Rubik's Cube. And the fastest non-human solving is by CubeStormer 3, which is 3.2 seconds. And every legal permutation can be solved in 20 moves or less. So the 20 is which called the God's number. Okay. And there are 43 quintillion possible permutations. Okay, so the advertisement says that a Rubik's Cube has millions permutation, but it is quintillion. Okay, so these two are my links of my, so the first one is my GitHub, and the bottom one is the PyCuber project. And welcome to pip install PyCuber. Okay, so any questions?
Just 2 quick questions. I'm still learning Python.
Yeah.
When you define the formula class,
Yeah.
you put a list inside the parentheses,
Oh,
but then you rewrite all of the methods
yeah.
that you inherit from list.
Oh. Oh, yeah.
So it,
Really?
am I right? Am I wrong?
No, you're right.
Okay.
Yeah, so actually I can do it like I can simply just don't extend that method. But at the first I just
That's where you started from. Yeah, that makes sense.
Yeah, that makes sense.
Okay.
Yes.
And so the optimize is really the difference between a mathematical or computer solution and a human being's manipulation, right? Because the optimize just gets rid of things that don't actually matter.
Actually, the optimize function is not like if you are doing a repeated move, and it will always return to the original state. Like there is a finger shortcut called RU R prime U prime, and if you do this formula 6 times, and it will back to the original state. But in PyCuba it won't optimize this, because PyCuba doesn't know that it will turn back to the original state. Well, the optimizing is that I will optimize like doing R, and that's completely do nothing. So I just delete them all. Okay, so R just return to the original state. Or R2, it will become a R prime. Yes. Did I answer your question? Yes.
Thank you so much for your sharing. I'm just very curious about how long have you been learning Python?
Oh yeah, I'm learning Python for 2 years.
Oh.
I don't know, 2 years and a half.
So I just want to say you're quite a genius. And how long have you been jumped in there for this project, PyCuber?
Actually, this project, I wrote a prototype about, I think it's 1 year ago, and then because the code was just spaghetti, but so then I wrote a structured program, which is in the list version. If you're going to GitHub, you're seeing the structured version. So this version is approximately, I think, 8 months ago. Yeah.
Oh yeah, wonderful, awesome. Thank you.
Thank you.
Any other question? Okay, I have a really simple question, quick one.
Yes.
That in the beginning of your presentation, you showed us a console with really interesting 3D plotting by ASCII,
Yes.
right? So does this code also inside the PyCuber?
No.
No, right? Because I just checked that. So why?
No. This project is not mine. Yeah. Yeah. This project is I forked it, but yeah. This project is called Rubicon. It's not a Rubicon yet. It's called.
Is that a joke?
Ruby, it's written in Python. Okay.
Okay, that's good.
Rubicon. Yes.
All right.
It's not this. This one. Yeah.
Okay. Cool. Thank you.
Yeah.
Really, thank you to know that it's written by Python. And anyone else? We still have 2 minutes, so I think we have one more question. No. Okay, then take a 2 minutes break. Thank you, Andrew, again.
Thank you.